Okay, the final thing I need to speak about is another formula. I'm not even sure what the name for this formula is, but it's an analog to Cauchy's integral formula, but for derivatives. Um, so I guess you can think of it as being the extended version of Cauchy's integral formula. So maybe I'll write um, Cauchy's integral formula, extended version, I guess. Okay, so it's essentially just another formula. What it says that if you have the same conditions satisfied as for the regular Cauchy's integral formula. So what I mean by that is you have some closed contour C, and you have a function f, which is analytic within C and on the boundary of C. And of course, as you'll see momentarily you'll need f to be uh, repeatedly differentiable. So let's say if it's n times differentiable, then you have the following formula. Nth derivative, so when you see f and then you have brackets n in the power, that doesn't mean f to the power of n. That just means the nth derivative of n. So if you had f and then in the power you had brackets 3, that would mean the third derivative. Anyway, the nth derivative of f evaluated at z naught is equal to n factorial over 2 pi I integral over c f of z minus z naught to the n plus 1. So this is a really nice result as well. But its application is straightforward. Again, it's just a formula. So I think if I just show you one example, hopefully you should have you should get an idea of how you would apply this formula. So as an example, let me do I'm going to compute the integral of sine z minus I cubed dz. And I'm going to take C to be the circle of radius 2. Going counterclockwise or anticlockwise. Okay, so similar to what we had before, so I draw my complex plane. I've got a circle of radius 2, and C is going counterclockwise. And the idea here is, I think in this case it's sort of clear what we need to take our interior point to be, right? Because on the denominator we have z minus z naught, and the function we have z minus I. So it's sort of clear we should take the interior point to be I, which is here, right? And we should let f of z to equal sine z, right? Now again, sine is an entire function, so it's going to be analytic everywhere. So of course it's going to be analytic inside and on C. And obviously we can see that I is an interior point. It follows by So I guess I'll call it extended CIF. Like I said, I'm not really sure what its actual name is. But anyway, it follows from that formula I have there that Fn I is equal to n factorial 2 pi I f of z on z minus I to the n plus 1 dz. Or in other words, I got this. So now when I write it in this form, I think to myself, well, what should I take n to be? It's clear that because I want z minus I cubed on the denominator, and I have z minus I to the power of n plus 1, I need n plus 1 to equal 3. So I should take n to equal 2. So if I take n equals 2, this tells me that the second derivative evaluated at I is equal to 2 factorial over 2 pi I c sine z minus I to the 3 dz. Now remember, we defined f to be sine of z, right? So the second derivative, well, the first derivative is cos, second derivative will be negative sine. So I have negative sine of I. Now 2 factorial just equals 2, because it's 2 times 1. So 2 over 2 pi I will be 1 over pi I. And now I just rearrange. So I'm going to get pi I, or negative pi I. Maybe I should make that clearer. Negative pi I times sine of I, right? And by definition of sine, sine of I will equal e to the negative 1 minus e to the 1 on 2i. So the i's will cancel, and your answer will be the following. And that's your answer there. And that's pretty much how you would handle that sort of a question. So, I mean, if you have something that resembles, when you look at it, it resembles Cauchy's integral formula, but you have a power appearing on the denominator, perhaps this is the way to go. Yeah, that's pretty much it.